Here we're going to do a linear correlation and multiple linear regression lecture, all in Microsoft Excel. I have some data here from the 2011, 2012, and 2013 seasons of Major League Soccer here in the United States. What I've done with the data is for each team, I've divided the data into information about the first 17 games of the season, that'd be the first half of the season, and some key information about the second half of the season. We're going to assess how information from the first half of the season correlates to and predicts information from the second part of the season. The first step is to look for linear correlation that we may want to assess further using linear regression. So as a review, let's do a linear correlation test here for a few relationships. First, I'd like to know if the number of points the team earned in the first half of the season correlates well to the number of points a team earned in the second half of the season. In soccer, a team earns 3 points for a win and 1 point for a tie. In case you don't remember, to find a linear correlation, we use the CORREL function. Equals C-O-R-R-E-L. I'm going to select my first set of information, which were the points during the first half of the season, all the way down to the bottom there. That's E3 through E58. Then I'm going to use a comma, and I'm going to select the points. You see my comma in here. Now I'm going to select the points from the second half of the season. Let's go see what we have. I'm going to close my parentheses, and I see a linear correlation coefficient of about 0.42. That's not particularly strong, but let's see if it's at least statistically significant. Recall that to be strong, it would have to be close to 1. However, statistical significance may still be interesting. Let's create a t-test statistic to test whether or not the correlation is non-zero in our researcher's hypothesis, or if the correlation is basically nothing in the null hypothesis. There's the formula. We go equals the correlation coefficient times the square root of the sample size, which in our case I believe is 56, minus 2. So the square root of 54, if I wanted to write it straight in that way, divided by the square root of 1 minus the correlation coefficient squared. So you see that's the square root of 1 minus L6 caret 2, L6 squared. That test statistic of 3.36476 is on a t-distribution scale. We should be comfortable at this point with what t-statistics are extreme and which are not extreme enough to reject the null hypothesis. Anything well outside of the range of 2 units from 0 is typically statistically significant. To find the p-value, though, just to check, we can use our t-dist function. The first input is the test statistic. The second input is the degrees of freedom, which would be 55, or 56 minus 1 in our case. And the final one would be a two-tailed test. The p-value is quite low. It's less than 1%, and thus we reject the null hypothesis and accept that there is a statistically significant linear correlation here. So at this point, we can say, yes, there is a linear correlation between first half points earned and second half points earned, but no, it is not particularly strong. It's somewhat of a moderate to weak relationship. Teams that do poorly occasionally do quite well later on, and teams that start off quite hot occasionally do quite poorly in the second half. There are enough teams that deviate from the perfect correlation that we do not have a very strong correlation. Let's do this with one more or two more sets of data here, just to set ourselves up for the regression. Let's assess whether or not teams that get a lot of possession. In soccer, possession is how often your team has the ball as a fraction of the total either time or passes in the game, depending on which statistic you're using. If a team has a lot of possession, it indicates the team probably has the ball a lot, has the ball very frequently during the match. My linear correlation coefficient is equal to CORREL. I select all of the possessions from the first half, comma, all of the points from the second half. I end my parentheses, and let's look at that correlation. It's even worse. It's probably statistically significant. In other words, there probably is some correlation, but it's nowhere close to 1, leaving a lot of room for error in the sense that teams with high possession may not do well in the second half of the season, and teams with low possession may very well do well in the second half of the season. The test statistic there will be equal to, again, correlation coefficient times the square root of, I'll just go straight to 54 this time, divided by the square root of 1 minus the correlation coefficient squared. Again, the test statistic looks pretty extreme. We can guess that it's probably statistically significant at the 5% level. However, the relationship itself is not particularly strong. This is a review of linear correlation. Let's step it up now and do some linear regression. Here I've taken a specific correlation that we didn't look at last time that I want to look at this time. It's still the same 56 teams over the past 3 seasons. We still are looking at the points that each team earned in the second half of the season. However, our first variable will now be their shot difference in the first half of the season. In this first case here, we see that Chicago earned 30 shots more than its opponents during the first half of the season, while Chivas during the 2011 season earned 16 fewer shots than its opponents. It may be that teams that earn a lot of shots early in the season are likely to earn a lot of shots later in the season and eventually score goals and earn points. Let's check that relationship using a multiple linear regression. First thing I'd like to do is I'd like to plot this as a scatter plot. So I'm going to select, using my mouse here, both columns of information, including the headers. I'm going to insert a scatter plot. I'm going to click the first option here. And now I have a visual representation of the relationship. I see a vague positive relationship here. Vague in the sense that not all of the points are right smack on a perfect line, but there is an obvious positive relationship. Positive because as the x variable goes up, the y variable tends to go up too. In other words, as teams earn more and more shots than their opponents, they tend to earn more and more points as a team in the second half of the season. To insert a trend line or a regression line, just to have a look visually, select a couple of your points here by clicking the left mouse button, and then right-click Add a Trend Line. We'll choose a linear trend line, and there you have it. This is the line that best summarizes the data points. In other words, it creates the linear relationship between the data points as close to a line as possible with as little error as possible. This point down here might be considered the most erroneous point. It has the largest distance from the line, indicating that this line is not a very good estimation for this team, nor is this line a very good estimation for that team. However, most points are reasonably close to the line, making this the line of best fit, or the regression line. Let's evaluate the regression now, looking at an output from Microsoft Excel. I'm going to go to my Data tab, Data Analysis, and I'm going to choose my regression option. In this case, for linear regression, we actually care what our y variable and x variables are. In regression, we are trying to estimate or predict a y variable from knowledge of an x variable. For our example, we're trying to predict the number of points a team will get in the second half of the season from the knowledge of their shot difference in the first half of the season. So my y variable will be my column of points in the second half of the season, and my x variable will be a column of shot differences in the first half of the season. This is true for any linear regression, regardless of what your variables are. Notice here that because I've selected the first row of each column, I need to click the labels box. Next, I need to choose where my output goes. So I click the output option, I click the open box, and I'd like my output to go right here in cell E1. So it's right next to my data. Now I press OK. It's telling me that it's going to overwrite existing data, but I know that it's not. So I'm going to go ahead and post it here. The output at first can look very intimidating. but we're going to focus on some of the key numbers you need to know from this output and what they mean. Let's go down here to some of my key values. The p-value is probably the first most important thing. The p-value tells us if there's a linear relationship at all. Recall that linear correlation told us that also, but linear regression can tell us the same information as well as additional information. Linear regression is like correlation on steroids. The p-value can be found up here under the significance F. For those of you using a Macintosh and Stats Plus, it may actually be called a p-value. Either case, that's the p-value. You may notice that it says E negative 0.05 at the end, which means we need to move this decimal point 5 places to the left. That's a very low p-value, which means that our level of significance is quite significant. We're well below the 5% level, for example. So the p-value is about 0.00003, and that tells us that there is a statistically significant relationship. The next most important value is the r-squared value. I'll show you where that can be found right here. The r-squared value in our case is 0.277. What that means is that nearly 28% of the variance in our y variable, that would be the variance in second half points, I'll call that y, can be explained by the variance in first half shot differentials, which is our x variable. For any x and y variable, this is what the r-squared value means. It's telling us what percent of the total variance can be explained. We'd like to explain 100% of the variance. A correlation or regression that is able to explain 100% of the variance in a y variable means that we can perfectly predict that y variable. Having that information may be very important for future decision making. In this case, the percentage is not high, but at least it tells us that knowing something about a team's shots can tell us something about how well it does in the future. Next up, we have the regression equation. Remember how I showed you that trend line at the very beginning of the linear regression portion of this lecture? That trend line can be calculated if we know what the slope and y-intercept are. Every line can be defined by its slope and its y-intercept. Right here, you'll find your intercept under the coefficients column, intercept row. Our y-intercept in this case is 23.35. The slope, which is oftentimes called m in your first algebra class, and we'll call it beta 1 in this class, the slope can be found right underneath the shot difference row. Notice that we've labeled the x value, the x variable here, shot difference, and right next to it, the slope shows up. To create a linear equation, you simply say that y equals the slope, 0.097, times your x variable, in our case that's shots, plus your y-intercept, 23.35. That's our regression equation. If we wanted to try to predict how well a team would do in the second half, and we knew how many shots it got more than its opponents in the first half, we would simply slide that shot difference in for x and calculate the predicted y value. This gives us an ability to predict the future, and we can predict it even better the better our r-square value is. So our r-square value isn't great, but it says that we can predict some of the future variance in team point earnings of the second half of the season. I might ask you to, for instance, predict the points earned for a team that got 25 more shots than its opponents. Here's how you would do that. You would say that y equals, and then you use your slope, 0.097, times 25 shots, that's our x value, plus 23.35. Now, Excel doesn't know you want to add this up, but at the very least, this is how you do it on a test. If you want to add it up in Excel, you say equals the slope cell times 25 plus the y-intercept cell. Thus, a team that gets about 25 shots during the first half of the season, more than its opponents, is likely to earn about 26 points in the second half of the season. Next, let's interpret the slope and y-intercept literally. Recall that the slope in this case is 0.097. What does that mean? If you go all the way back to your first algebra class in kindergarten, you know that slope is a change in y over a change in x. In this case, it is a 0.097 unit change in y divided by a 1 unit change in x. To interpret that in real terms, we would say that for each additional shot earned in the first half, that's our x, technically it's our change in x, we expect 0.097 additional points in the second half of the season. That can be extrapolated if we want to talk about more than just a one-shot change. I could say for each additional 10 shots earned in the first half of the season, that's my 10-shot change in x, we expect 10 times as many additional points. So if you do the math on that, you'll see that for every additional 10 shots earned in the first half of the season, a team is expected to earn an additional 0.97, or almost a full additional point, in the second half of the season. You'll notice that in our data set over here, one of our best teams, Sporting Kansas City, in the 2012 season, had 102 additional shots over its opponents. In other words, it had 102 more shots than its opponents had against it. We might say for Kansas City that a extra 102 shots earned in the first half of the season expects 102 times 0.097 additional points. That's nearly 10 additional points in the end of the season over what an average team would get. Sporting Kansas City had a good 2012 season and an even better 2013 season. In 2013, we see that it also had quite a few additional shots, and in 2013, it won the championship in Major League Soccer, known as the MLS Cup. The y-intercept in our case was about 23.35. We saw that up here. This is the expected y value when x equals 0. In our case, it's the expected number of points when a team gets just as many shots as its opponents. So a team that has exactly 0 shots more than its opponents, basically a team that breaks even in terms of shots for and shots against, is likely to get that many points in the second half. That's what a y-intercept means literally, is if you set x equal to 0, what is your y value? That applies to linear regression also. The last thing I want to talk about here is the standard error. The standard error is a measurement of that distance between each of the points and the line. Recall the trend line we saw earlier. Some of these points were very far from the line, like this one. Other points were almost right on the line, like this one. The standard error helps us to tell about what the average distance from the line is. It's kind of like an average error. Technically, it's a standard deviation of error. You'd like your standard deviation of error to be quite small. That means that the line is an adequate prediction of all of the things that happened, and would likely be an adequate prediction of all of the things that will happen in the future. This line is not perfect by any means, as there are quite a few errors here, quite a few points far off the line. If we go look at the standard error, which can be found right here at the top of the output, we see that any prediction for a team is subject to an error, or an average error you might say, of about 6.3 points. That's quite a few points in the second half of the season. Last year in the Eastern Conference, playoff teams were separated by only about 9 points. So when you have an error of 6.3 points either direction, that's a lot of error, and it makes the predictions not quite as helpful as they could be. Interpreting standard error is difficult unless you know the y variable's context. Some of you may not be soccer fans, and to know that the error is 6 points doesn't really help you all that much. You don't know how much 6 points really is. If I give you an example where you're supposed to predict a student's grade, or you're supposed to predict the sale price of a house, then you may be more likely to understand what a good error is. If I tell you you're going to get a grade and I tell you the error is about 2 full grade levels, that's not very helpful because I could tell you you're going to get a C, but you might get an F or you might get an A. That's a lot of error. If I instead told you that I was going to sell your house and I think I could sell it for $200,000 plus or minus $5,000, that error of $5,000 is really not that much. That gives you a very good number to plan on when you know how much you're going to get for your house. So interpreting the standard error is completely contingent on your understanding of the y variable itself. We'll do more examples in these lectures in which you may be more comfortable with the y variable. Here we can say the standard error of 6.3 points is quite large, as often 6.3 points separates the best teams from the average teams.